Hello everyone, this is Mustafa with the electronics video on batteries. In this video we're going to cover the kind of big important ideas and important specs for FRC when we look at batteries in the FRC point of view. There's a lot of really cool chemistry and physics that go behind batteries, so if you want me to cover that, let me know. I can make another video about it. But anyways, here we go. Alright, so batteries to me are this like super magical and mystical thing. It's crazy like how they work. This is like you have this little capsule that kind of power your robot. It's pretty cool to me. But it's also a source of like a lot of paranoia because if the battery goes wrong on a robot, like during competition especially, you're gonna lose the match, right? Because if you can't move, if you don't have power for your robot, your robot can't do anything, right? You're gonna lose the match. Um, and so because it's a source of paranoia, and I bet it's a source of paranoia for a lot of our teammates, right? By understanding the factors that impact battery performance, we can kind of soothe our anxieties a little bit and be a little more at peace, right? All right, so the two main types of batteries we have at Skyline right now are the interstate batteries, SLA1116, and the MK batteries, right? So the interstate batteries, they're usually the older ones. Recently, we're kind of switching over to MK, but if you ever see interstate batteries, usually are practice robot battery, and the MK batteries are comp robot batteries, right? Yeah. Okay, so before we get into kind of the specs and kind of understanding how batteries work at a higher level, um, I want to kind of talk about how we go about wiring, kind of attaching those wires to the batteries. All right, so we're going to start off with kind of 6 or 4 gauge piece of wire, and we're going to strip insulation on both ends. Right? We're going to strip the amount enough so that the crimp can kind of completely slide on. Right? So the first crimp we're going to put on is the compression lug, and we're going to put that on one end. The thing with compression lugs are they're very hard to crimp, right? I think I remember like last year, 2020, I had like Vibhav and Arnav jump on the crimp in my garage while I kind of held the crimper on my steady, and they can be like notoriously difficult to crimp. Just be aware of that. In the build room, you can kind of try to use a vice grip to kind of get enough mechanical advantage to crimp them easily. All right. The second crimp we're going to attach is the SP50 contact. They look like this. And these ones are much easier to do, right? We just use our Anderson crimper and they're pretty good to go. Or you can use the larger crimper also. I can show you this in the build room if we ever go back. All right. Then you're going to heat shrink, right? So we're going to cover any excess wires or excess strands with the heat shrink. And something to be aware of when you do attach the crimps is be sure to get all the strands inside. Remember, if you remember from our video on resistance, right? Depending on the cross-sectional area of the wire can impact resistance. So we're going to be sure we get all the strands inside to kind of minimize the resistance in our wire. And so we're going to heat shrink the two ends. And then we're going to attach your SP50 connector. And so the SP50 contact has this little hook looking thing right here. And that hook attaches onto a metal plate in the SP50 connector. So if you've done it right, you'll see that hook kind of latch on, and you won't be able to pull it out by yanking on it. So that's the SP50 connector. And on the other side for the compression lug, you're gonna kind of tightly screw it onto the battery terminal. The battery terminals have these holes in it, so you're gonna kind of use a screw-in bolt and nut and a washer to screw it on, nice and tight. You're gonna heat shrink the terminal part and kind of wrap it with electrical tape to make sure there's no metal exposed. You don't want any shorts, right? And yeah, so that's how we wire a battery. Okay. And it's another side note, right? Batteries are made of some really nasty stuff, right? The things we have are lead, and lead is very poisonous. So please, if a battery leaks, just be safe, right? We don't want to eat our batteries. We don't want to touch our batteries. We don't want to get any of the inner battery stuff on us, right? And if it does happen, our safety captain Abby probably knows a lot more about this, but we have a spill kit. And the spill kit helps us kind of manage any battery acid leaks and kind of safely dispose of it. All right, so just beware, batteries can be pretty nasty. All right, so let's go on to some battery specs. All right, so the first thing I'm going to talk about is nominal voltage. And nominal voltage is a measure of the electromotive force between the battery terminals. So these two things right here are our battery terminals. And if you don't remember what EMF is, I highly recommend you go watch part 2 of our DC motor series. But just a quick kind of debrief, or quick review, sorry. A potential difference is when you transfer electrical energy into some other form of energy. For example, a light bulb transfers electrical energy into radiation. However, EMF is when you do the opposite. It's when you take some other form of energy and convert it to electrical energy, right? In the case of a battery, it's converting chemical energy into electrical energy. That's why it's an electromotive force, or EMF, okay? So the nominal voltage for all FRC legal batteries is 12 volts, right? That means for every coulomb of charge that the battery emits, there's 12 joules of energy behind it. Okay. And another spec you'll see is the chemistry. Okay, so all FRC legal batteries are lead acid batteries. There are other types of batteries in the world, like we have nickel cadmium, nickel hydride, lithium ion, lithium polymer, and there's a whole bunch of other ones. They all have some advantages and disadvantages. But for lead acid, the main advantage is that it's more resistant to life-shortening factors, right? So batteries often, a lot of batteries, they have some gassing issues where the chemical reactions release gas, and you'll see the battery puff up. Some of the batteries are a lot more volatile and can easily explode or leak if not handled properly. So lead acid batteries are really resilient, and that's why we use them in FRC to last as long as we can. All right, so that's the chemistry. And you won't really see this frequently on the battery itself, but something I want to talk about is max discharge current. If you look at the documentation online, you'll find this. And I'll link the documentation for MK batteries in the description, so if you want to take a look for yourself. But max discharge current for our old interstate batteries is 250 amps. 250 amps for interstate batteries, and for MK batteries, it's 270 amps. Right. So this is way beyond what our FRC robots will ever draw at any point in time. But the reason I put this here is if a short happens between the terminals, the battery's in danger, right? Because remember, in a short, because there's very low resistance between the two terminals, and if you look at Ohm's law, right, that means we have a really high current draw between the battery, right, and which goes beyond the 270 amps. And this really high current draw, if sustained for a long enough period of time, can really do serious damage to your battery. So you're gonna be careful not to have any shorts on your robot. All right, so another spec is battery charge capacity. Okay, and this is kind of a measure of this charge stored in a battery. And the units for charge capacity is amp hours, right? Amp hours is equivalent to the charge delivered by 1 amp of current in 1 hour. And you might be wondering, right, we talked about charge in our first video with coulombs. Well, both coulombs and amp hours are a measure of charge, right? And just to show you this, I did some dimensional analysis, right? So remember, amps is charge over time, or electric current is charge over time. And so if we rearrange the equation, we get that charge is electric current times time, right? Where do we see electric current times time? Well, amp hours, right? Amps for electric current and time and hours for time is equal to the unit of charge. Okay, and 1 amp hour is equal to 3,600 coulombs, right? There's 3,600 seconds in an hour, so there's 3,600 coulombs in 1 amp hour. And just to show you what an amp hour means, I did an example with 18 amp hours, right? So if a battery has a rating of 18 amp hours, that means it can deliver either 18 amps for 1 hour or 1 amp for 18 hours. However, it gets a little more complicated than that, right? So the capacity of a battery changes depending on the discharge rate, right? So usually the faster you discharge a battery, the less charge becomes available. I have this snippet in the bottom right here. I took this directly from the MK documentation, but it says that if you discharge the battery over 20 hours, over a 20-hour rate, you have 18 amp hours of charge available to you. However, if I do it 4 times faster, if I do it at a 5-hour rate, I only have 15.3 amp hours available to me. Right. Sorry about my recording software timed out. But another spec you'll sometimes see in batteries is something called the battery energy capacity, right? And this is a measure of the energy stored in a battery. The units for this is watt hours, right? So the energy delivered by 1 watt of power for 1 hour. And again, this both joules and watt hours are equivalent. And again, I did some dimensional analysis just to show you this, right? So remember from physics, right? If you guys see in Gen Physics, we know that power equals energy over time, right? And if we arrange the equation, we get energy equals power times time, right? And where do you see power times time? Well, watt hours, right? Watt hours is power times time, and that's equivalent to energy. All right. And just to show you how we can, so amp hours and watt hours are very closely related. In fact, if we just take amp hours and multiply it by a battery voltage, we get watt hours. And like you ask, well, how does that work, right? Well, if you remember from a few videos ago, we talked about how power equals voltage times current. Right? So if we multiply amp hours times a battery voltage, we get power, right? So there's the same idea going on here. Okay. Now I'm going to talk a little bit about Now I'm going to talk a little bit about internal resistance and sulfation in batteries. Okay. So batteries all have an internal resistance, such like we had with motors, right? And we're trying to limit that internal resistance as much as possible. Just to show you an equation, right? The voltage output of a battery is the voltage EMF, so VEMF, minus the current being supplied by the battery times the resistance of the battery. Okay, we'll use this equation in this example problem just so you can see it in work. So the higher the internal resistance, right? If you have really high internal resistance, you're going to have longer charging times, which is not good, right? You're going to have excessive heating. And if you remember from our video about DC motors, right? The more you heat up a motor, the more the internal resistance increases. And that's the same for batteries. So you kind of have this positive feedback loop, right? The more resistance you have, the more it's going to heat up. And the more it's going to heat up, the more resistance you're going to have. And it's going to go up and up and up and up, right? So you don't want to have very hot batteries because that means you're going to have a really high internal resistance. And a high internal resistance also means you have shorter run times and shorter battery life, right? And for the kind of abuse we put it in our FRC robots, we want to be sure that we have as much of a battery life as we can to make sure it lasts through competition and through a match. And so for FRC batteries, right, our MK batteries are usually at 0.012 ohms. And that's pretty good. If anything's really above 0.016 ohms, it's kind of in the gray area, and it's better used for a practice bot. But anything under 0.016 is perfectly fine, and for competition. And if you're wanting the interstate batteries, they're usually around 0.012 ohms to 0.015 ohms, so they're a little higher in their internal resistance. But again, if it's under 0.016, you should be perfect for competition. All right, well, also we have this thing called sulfation. So sulfation is when there's some sulfur compound that builds up on the positive and negative plates of lead acid batteries. And this buildup can drastically increase the internal resistance of the battery. Right? And sulfation can occur when you store it in too warm of an area. So too warm is 75 degrees Fahrenheit and above. And for every 10 degrees Fahrenheit above 75, right, so say I stored it at 85 degrees Fahrenheit, sulfation will occur twice as fast, right? So to be sure, we store our batteries in a nice, cool area. Also, if it's left, so sulfation also occurs if it's left without charge for too long. Right, I'm kind of worried. Right now we're in quarantine, so I'm kind of worried for the batteries we have at the workshop at the build room right now because they haven't been charged for like about 5 months. So we might have a lot of sulfation happening with our new MK batteries. So we're gonna be sure we keep our batteries charged at full charge whenever we can. And a good practice is like whenever we have a meeting, just kind of swap out, because we have kind of limited terminals on our battery charger. Just swap out the batteries, make sure all the batteries have a chance to get to full charge. And also if it's left overcharged for too long, that a sulfation can occur. Our battery chargers have protections for this. So as soon as it detects that we have a full battery, it will stop charging it. But something to keep in mind. All right, and also terminal damage can cause a drastic increase in resistance and can sometimes completely ruin your battery, right? So, be very careful with how you handle your terminals, right? So here I have a picture of myself, Mustafa, right? I'm very bad at this. I almost always grab the wires when I'm carrying batteries. So when you carry batteries, be sure you carry it from the base and not from the wires, right? When you use the wires, you cause damage to the terminals. And I'm very bad at this. That's why you have a picture of me here holding by the wire. So don't be like me. Be like Vibov, right? Who holds the battery from its base. Be a good boy. All right. And something also to keep in mind that as a battery discharges, right, as it gives out charge, the internal resistance in it increases, and the voltage, the EMF it provides decreases, right? And this is kind of a chart that shows you that, right? So as we can see, as through these lines, right, as it discharges, the voltage for the battery kind of drops a lot. And from my experience with FRC battery, with an FRC, if a battery usually drops below 10 volts, you will see visible, like you can see the robot stutter and kind of shake around a bit because it doesn't have enough current to support its systems. Okay, and whenever you see a robot kind of do that shakiness or not have enough current to support all its systems, it's called a brownout, right? And we'll look at this when we do our software videos and look at driver station logs. But whenever you see a brownout, that means the battery wasn't able to provide enough current to support the robot systems. All right, the thing I want to talk about is a battery beak. It's just a really cool thing right here, and it's a little device that plugs directly into the ST50 connector and gives you information about the internal resistance of the battery, how much charge is inside in percentage. So usually you'll see it at 130%. That's just because when you directly take it out of the battery charger, it'll kind of read above 100%, which is perfectly fine. And it has some other important information, but the main thing is charge percentage and internal resistance. Those are the two things you want to look for. All right, I'm going to end with some example problems. Right, the first one is a battery is rated at 30 amp hours. How much current can it deliver if it's discharged over 3 hours? And the second problem is, I had a lot of fun with this one, so I hope you enjoy this. It's a little challenging. It's going to use a lot of the equations we've discussed in this video and in previous videos, so I hope you have fun with it. But before the robot entered the field, Abby beaks the battery to find that it has an internal resistance of 0.03 ohms. Surprised, she quickly swaps the battery with a different one of internal resistance 0.01 ohms. Assuming a battery releases a steady 50 amps for the 180 seconds match, how much energy in joules did Abby save by swapping the batteries? I'll give you a few seconds to pause. Alrighty, on to the first question. Right, so a battery usually at 30 amp hours, how much current can it deliver? If it's discharged over 3 hours, well, it's really simple. Current is going to be our 30 amp hour battery capacity divided by our 3 hours, and we get that the current it can deliver for 3 hours is 10 amps. All right. And for the second one, I kind of broke this down into 3 parts. For the first one is we're going to calculate the energy outputted for the high resistance battery, energy outputted for the low resistance battery, and then we're going to subtract to get the final answer, right? So to start off, we're going to use 3 equations. The first equation is power equals voltage times current. We discussed this again in a previous video if you want to take a look at that. Second equation is the one we had earlier on in the slides, right? That voltage output from a battery is the voltage EMF, the EMF of the battery minus the current it supplies times the resistance of the battery, the internal resistance of the battery. All right, and the third equation is energy equals power times time. And if you've taken any gen physics class, you probably covered that equation. All right, so I'm going to combine these 3 equations into one big boy equation. Energy equals current times voltage EMF minus I minus current times resistance of the battery, all times time. Right, so this equation right here. Plug in the values we know for the high resistance battery, and then we finally get that energy equals 94.5 kilojoules. Right. All right, I'm just going to take that equation we found and kind of plug it in for our low resistance battery. And Plug in the values we know, right? And we're going to get energy output of 103.5 kilojoules. And if we subtract, and for our final answer, we get that Abby saved 9 kilojoules of energy by simply swapping the higher resistance battery for a lower resistance battery. And this kind of shows you like 9 kilojoules is about 8% or 9% of the 103.5 kilojoules, right? So the internal resistance makes a big difference on battery life and the amount of power the battery can provide. So it's a big deal, all right? So that's about it for this video. I hope you guys enjoyed it. I hope it wasn't too complicated. And yeah, I'll see you in the next one.